Today we will continue to learn about image classification. Today we will learn about the CIFAR-10 dataset, and we will learn how to build an AI model to classify RGB images. Finally, we will learn what a convolutional neural network is. Today, we will build CIFAR-10 image classification AI with Keras. CIFAR is a global research organization based in Canada, supporting a wide range of research fields and research projects. CIFAR also supported building the CIFAR-10 image database. This database has been utilized for many deep learning algorithm researches. The CIFAR-10 dataset is a collection of images frequently used to train machine learning and computer vision models. The CIFAR-10 dataset consists of 60,000 32 by 32 color images. The total number of classes is 10, and each class has 6,000 images. This database has been widely used in machine learning technology research in the past and is still being used. CIFAR-10 images are color images. Also, like MNIST, the resolution of each image is very low. The resolution of the CIFAR-10 image is very small, as you can see. It is not easy to recognize with the human eye, but if you look closely, you can confirm that this image is an image of an airplane. The CIFAR-10 database is provided in the form of an ND array in Keras like MNIST. Create a file called CIFAR-10 classification nn.py and add the following code. CIFAR-10 data provided by Keras consists of image ND array and image label ND array. The labels of images are encoded as follows. Now, let's see how the CIFAR-10 image data is structured. Train input is the image data used to train the model. Let's check the shape of this data in the Python shell. CIFAR-10 data consists of 50,000 trained data. Also, the resolution of one image is 32 by 32. And unlike MNIST, the color information of one pixel in the CIFAR-10 image cannot be expressed with a single number. Instead, the color information in one pixel is represented by 3 numbers. Each number represents a red, green, blue value, and this information allows each pixel to make up a color image. Let's rewrite the code in the CIFAR-10 classification nn.py file as follows. Let me explain the code. First, let's look at the code in line 14. CIFAR-10 images are color images in RGB format. The value of each color is expressed as an integer between 0 and 255. When this value is divided by 255, the color values are converted to a value between 0 and 1. Adjusting the range of input data like this is called normalization. Normalization can reduce the training time of the neural network. All other codes are things you learned in the previous class, so you should have no trouble understanding them. However, the method called summary in the 23rd line is something new. When the model.summary method is called, it prints the structure of the compiled model to the console. Now, write additional code in the CIFAR-10 classification nn.py file to complete the program. The full code can be found on the course page. When you run the program, training starts and the following text is printed to the console. Although the inference result and the correct answer for 5 test input are the same, if you evaluate the entire test data, you can confirm that the model's accuracy is about 53%. How can we improve the accuracy of the model? In this lecture, we will learn about convolutional neural networks and use them to improve the performance of the CIFAR-10 classifier. In the case of the currently implemented model, the input image data is made into a one-dimensional array and passed to the dense layer. This will turn the image into a single line of color band. If one image is cut into several thin lines and joined together, it will be difficult for people to guess what the original image looks like by looking at the stripes. The same goes for neural networks. When an image is flattened and input to the neural network, it is difficult to convey information about the shape of the image. To solve this problem, let's take advantage of what's called a convolutional layer. Convolutional layer is a layer that passes the convolution of input numbers to the next layer. The image below will help you understand how convolution works. The convolution operation utilizes a constant matrix called a kernel. Algorithms for setting numeric values inside the kernel have been developed by AI researchers. And if you check the output of the convolutional layer, you can see that the dimension of the input value does not change. A kernel is a matrix used for convolution with the input. If you use Keras, you can specify the size of this matrix as an argument. A filter is a function that defines the numbers that make up the kernel. Although AI researchers have created various filter functions, you do not need to understand these functions mathematically. In Keras, even if you do not specify which filter function to use, the numbers inside the kernel are set through the default filter function. The number of filters can be several. In this case, several matrices are created from the convolution operation, and all these matrices are passed to the next layer. Images passed through the convolutional layer become smaller fragments, and the number of these pieces is equal to the number of filters. If you look carefully at the matrix that comes out after performing the convolution operation, you can see that the composition of the matrix numbers is similar to the input. In addition, the dimensions of the data passed through the convolutional layer are preserved. Therefore, the convolutional layer is used as a layer that preserves and compresses the spatial relationships of the input data. The pooling layer is mainly attached after the convolutional layer to reduce the size of the incoming data. In the pooling layer, input data is sliced, and then the data in the slice is reduced to one value. This value can be set as the largest value in the slice, or as the average of the values in the slice. A new output is then created with the values of the slices. Now, create a code file called CIFAR-10 classification CNN.py and write the following code in this file. The code is also posted on the course page. Let's start by explaining the first parts of the code. In line 18, we can see that the conv2d layer is used. Conv2d layer receives two-dimensional data, performs convolution operation, and passes the result to the next layer. If you read the 18th line, you can see that a total of 32 filters are used, and the size of the kernel is 3 by 3. However, you may find it strange that the activation function is also used in convolutional layers. This means that each value in the matrix that comes out after the convolution operation is passed to the activation function. As mentioned earlier, there are several pooling methods. Among them, max pooling is a method of passing the largest value of a slice to the next layer. In the code, the size of the slice is 2 by 2, and the max pooling 2D layer was used because a two-dimensional image was input. And the activation function is not utilized in the pooling layer. Since the data that has passed through the pooling layer is still two-dimensional, flattening must be performed to transmit it to the dense layer. Since the data has already been compressed while reducing the size of the original image, it becomes easier to understand the meaning of the data, even if the output of the pooling layer is converted to one dimension. Let's train the model for 50 epochs and evaluate the model's performance with test data. As shown below, you can see that the performance of the model has improved compared to the previously implemented neural network. Since an image is two-dimensional data, it becomes difficult to understand the meaning of the data after flattening unless spatial information is compressed and the size is reduced. However, if the convolutional layer is used, the size of the 2D data can be reduced by compressing it, and it becomes easier to understand the data in the next layer even after flattening it. And although the performance of the model has improved compared to before, it seems that it's still necessary to improve the accuracy of the model. Scientists have created neural networks with many layers to improve the performance of neural networks. Such neural networks are called deep neural networks. Let's see whether creating more layers improves the performance of the neural network. As you can see in the slide, let's create a neural network with multiple convolutional layers. Write the following code in a file called cfart10 classification dcnn.py. Save it and run it. If you run the program, you can see that the accuracy of the neural network is improved by 3%. If you want to find the appropriate training epoch value for the neural network, check the model's performance by assigning several values to the epoch parameter. In general, too large epochs are not recommended, and when the amount of data is small, it is recommended not to train with too few epochs. The neural network implemented earlier also shows about 68% accuracy. When designing a model, you can try various experiments yourself, but the performance of the neural network does not improve by just making more layers. Like this, neural network modeling is not easy. To design a neural network yourself, you need to study a lot. However, even if you don't know how to design the structure of the neural network, there is no problem in using AI technology, because you can use models designed by other people. Even if you're not familiar with math or computer science, you can take advantage of AI technology. Even if you don't know how to design a neural network, you can build an AI that can do specific tasks by using an open source library or model. And the neural networks used these days have much more layers and are much more complex than the neural networks we implemented today. So to take advantage of these models, you need a GPU unit with a large VRAM. This is the end of today's lecture. In the next lecture, we will learn about the image classification application and Keras.